In wide sky surveys, the first sign of a new small body does not arrive as an announcement, but as a faint point that refuses to match the stillness of the background. A telescope returns repeated images of the same patch of sky taken minutes apart, then again on later nights. In each image, the stars hold their geometry with near-perfect patience, while certain points shift by a small, consistent amount. The discovery process begins with that difference. Software compares images, subtracts what remains fixed, and flags what changes. Most flags are discarded quickly. Some are cosmic rays that strike a detector and leave a single bright pixel. Some are satellites that cut thin lines across the field. Some are known asteroids whose positions are already predicted. The remaining candidates are tested by repetition because a discovery is not a single measurement, but a pattern that persists across time. The point that becomes 3i Atlas enters the record through this discipline. Its presence is defined first by coordinates and timestamps, not by interpretation. Each detection is an estimate of where the object lies on the sky at a specific moment tied to the observatory's clock. The clock matters because the object is not simply located, it is located at a time, and its motion is inferred from how that location changes. Even the method of finding the center of the light matters. A faint object has a soft edge. Its image is spread by the atmosphere, and the optics and noise in the detector adds small fluctuations. The centroid, the measured center of the light distribution, is an estimate that becomes more stable when the object is bright and sharper, and less stable when the object is faint and diffuse. Early detections often sit closer to the boundary between signal and noise than later follow-up observations do. So the first positions are valuable but also delicate. Astrometry then ties those pixel positions to the sky. Each survey image contains many background stars with catalogued positions. A transformation is computed that maps the detector grid into celestial coordinates by matching measured star patterns to their known positions. This transformation must absorb small distortions from optics temperature and mechanical flexure. It must also handle the fact that the atmosphere refracts light-shifting apparent positions slightly toward the zenith in a way that depends on altitude above the horizon and local conditions. The pipeline applies corrections, but corrections are never purely abstract. They sit on measured or assumed values of pressure, temperature, and humidity, and on models that are good but not perfect. The result is a set of right ascension and declination values for the moving point, each paired with the time of observation. From the outside, a discovery can seem like a single dramatic moment. In practice, it is incremental because the candidate must be confirmed. Confirmation means an independent observation that sees the same moving point close to where the first measurements predict it will be. This prediction can be crude at first. With only a short arc, a few detections across one night or 2 nights, many trajectories can fit the data. The earliest prediction may define a search region on the sky that is large enough to be uncomfortable, especially if the object is faint. Yet surveys and follow-up stations work together. One station reports its measurements, another targets the predicted region, and if the object appears again, the orbit estimate tightens. The object becomes less of a candidate and more of a tracked body. The label attached to the discovery is part of that network. It points to the reporting stream and the fact that the object's identity is tied to a growing set of measurements rather than to a single image. In the earliest phase, 3I atlas is a line of points, and every added point changes the line slightly. The motion is seen first as a shift across the star field, then as a rate of motion, then as a curvature in that motion as days pass. The curvature matters because it is one of the ways distance becomes constrained. An object's apparent drift on the sky is shaped by its own motion and by Earth's motion. Earth rotates and translates around the Sun, and that change in vantage point introduces parallax for nearer objects. Over multiple nights, the combination of Earth's movement and the object's movement creates a signature that helps separate a nearby fast mover from a distant slow mover. This separation is never perfect at first, but it improves with time. Brightness enters the story early as well, not as an aesthetic quality, but as a practical constraint. A faint object demands longer exposures or larger telescopes for follow-up. It also invites caution about false positives and centroid bias. If the object appears slightly fuzzy compared with nearby stars, the fuzziness could indicate a coma, a surrounding cloud of dust and gas, or it could indicate poor seeing defocus or trailing during the exposure. Survey images are not always taken with the moving object as the primary target, so exposure times and tracking rates are optimized for coverage rather than for a single faint body. Follow-up observations can be designed more carefully, but early in the process, the data set is mixed. This mixture matters later when analysts examine residuals and wonder whether the object deviates from prediction. A deviation can be created by subtle differences between instruments and reduction pipelines, especially when the object is faint. The discovery stage therefore holds two parallel tasks. One is to prove the object is real and keep it in hand. The other is to build a trustworthy measurement foundation that will not create illusions later. Observers record not only the positions, but also the circumstances, which telescope, which filter what air mass, what exposure time, what apparent motion rate. These details are not decoration. They allow later analysts to check whether a subset of data carries a consistent bias. If a dramatic claim emerges later, it can be tested against whether the earliest data come from a regime where systematic errors are more likely. In this outermost region, the tidal language that suggests weighting is not part of the measurement. The sky survey does not see weighting. It sees detectability. An object is detected when it is bright enough against the background, when it is in a surveyed area, and when its motion signature passes selection thresholds. An object can be present and still go unnoticed if it is too faint, if it lies in a crowded star field, if it sits too close to the sun in the sky, or if its apparent motion is too slow to be flagged. The discovery moment, therefore, is not the object's arrival into existence. It is the point where the observing network becomes sensitive to it. The object's path has been unfolding long before the first detection, and the discovery simply marks when the path intersects human coverage and human thresholds. By the end of this first stage, the object is a small moving point that has passed the first tests of consistency. It appears again when predicted, and its reported positions begin to form a coherent track. The arc is still short, and uncertainty is still wide, but the object is now anchored to a shared measurement record. This record is the only safe beginning. It contains no intention and no metaphor, only a quiet accumulation of coordinates and times that will later support more detailed questions about whether the motion fits a gravitational baseline whether residuals persist, and whether any additional forces must be considered. For now, the object is simply there, measured carefully, and held by continued observation, so that the next inward steps can be taken on solid ground, rather than on an early impression. From the first detections onward, the object exists for observers as a sequence of directions on the sky. Each measurement is an angle, not a distance. Right ascension and declination describe where the object appears on the celestial sphere at a specific moment. The geometry that turns those angles into a trajectory begins by acknowledging that the observer is moving. The telescope sits on Earth, and Earth rotates, carrying the observatory through space. Earth also travels around the Sun, changing the line of sight over days and weeks. The object's own motion combines with these movements, so the apparent track is a braided result of several motions at once. The task here is to translate an apparent drift among stars into a physically consistent path in 3 dimensions, without leaning on story language and without assuming that a slow change implies anything beyond geometry. The first step is to treat each position as a line of sight vector. A measured right ascension and declination define a direction from the observer toward the object. If that direction is expressed as a unit vector, it points along a ray that extends into space. The object lies somewhere along that ray, but the distance along it is unknown. With multiple measurements, multiple rays exist at different times from different observer locations. The object's path must intersect those rays at times consistent with its motion. Early on, with a short arc, many 3-dimensional paths can satisfy that requirement within measurement uncertainties. This is why orbit determination is iterative and why uncertainty is not a side note. It is central. The geometry does not yield a unique answer until the observing arc becomes long enough and the viewing geometry diverse enough. Parallax is one of the main geometric levers. Parallax is the apparent shift in position of a nearby object when viewed from different locations. Earth's size provides a baseline across a night as the observatory rotates around Earth's axis. 2 observatories at different longitudes also provide a baseline because they view the object from different points on Earth at roughly the same time. Over days, Earth's movement around the Sun provides a much larger baseline. For nearby objects, parallax can be significant and can curve the apparent track over a single night. For more distant objects, parallax is smaller and the apparent motion is dominated by the object's own velocity projected onto the sky. Observers use the way the apparent motion changes with time to infer distance, but the inference is not immediate. It requires enough observations that the parallax signature can be separated from the object's own changing direction. Timestamps make geometry actionable. An object observed at one time and then again later does not simply shift by a certain angle. It shifts by that angle over a specific interval, and the rate of change is a clue. If the object is close, it can move quickly across the sky. If it is far, it tends to move more slowly. Yet geometry complicates this, because a far object can appear to move quickly if Earth's motion produces a strong apparent change in direction, and a near object can appear to move slowly if its velocity happens to align in a way that produces small angular change. This is why rate alone is not diagnostic. Curvature and changing rate over time carry more information. The aim is to gather enough points to see whether the track on the sky is straight or curved, whether the curvature changes, and whether the pattern matches expectations for a body moving under gravity. The conversion from sky coordinates to a trajectory also requires careful attention to reference frames. The observatory's reported position is tied to Earth's surface, but orbit computations are often done in an inertial frame that does not rotate with Earth. This requires transforming the observer's location from Earth-fixed coordinates to inertial coordinates at the time of observation. The transformation includes Earth's rotation and small changes in Earth's orientation. It also requires that the time scale used in the transformation matches the time scale used in planetary ephemerides. A small mismatch can produce small systematic errors. These are the kinds of errors that become important later if claims are made about subtle deviations. In this region, the work is to ensure that the geometry is built on consistent timing and consistent frame definitions. Light travel time adds another layer. The observed light left the object earlier than the observation time by an amount equal to the distance divided by the speed of light. For solar system distances, this delay can be minutes to hours. In precise modeling, the predicted position of the object must be evaluated at the emission time rather than the reception time. This correction is standard and is included in orbit work, but its presence reminds that geometry is not only about positions and velocities, it is also about aligning events in time. Aberration adds yet another layer. Because Earth is moving, the apparent direction of incoming light is slightly shifted. This too is corrected. Each correction is small, but the point is that an accurate trajectory is constructed by stacking many small corrections, so that residuals do not later masquerade as mysteries. Uncertainty propagates through geometry. Each astrometric point has an uncertainty that may be different in different directions. A faint object may have a larger uncertainty. A high air mass observation may have a bias. A crowded star field may increase error. When these points are combined, the uncertainties do not simply cancel out. Random errors can average down, but systematic errors can persist. In early orbit solutions, the uncertainty region on the sky for the next night can be large, reflecting the fact that many trajectories remain plausible. As more data arrive, the uncertainty shrinks and becomes more structured. It often stretches along one direction more than another because certain combinations of parameters remain correlated. These correlations are not mistakes. They are the mathematical expression of what the data cannot yet separate. The phrase "waiting in a physical translation" can refer to a geometry where apparent motion is slow, where the object remains in a certain part of the sky for a long time, or where the line of sight changes only gradually. Such conditions can arise naturally. If an object is far away, its angular speed may be small. If its motion is aligned such that it remains near a particular elongation from the Sun, it may be observable in a similar region across many nights. If the object's orbit and Earth's orbit produce a geometry where relative motion is low, the object can appear to linger. None of this implies intention. It implies the relative velocity vector projected onto the sky is small and changes slowly. The geometry can create the impression of residence. It can also create challenges for orbit fitting, because slow motion yields less information per unit time about distance and curvature. In addition, survey coverage introduces another kind of apparent weighting. A survey observes certain regions more often than others. Regions near the ecliptic, the plane of the planets, are often heavily monitored because many small bodies lie there. Regions near the sun and the sky are hard to observe. Regions near the Milky Way can be crowded and difficult. An object can be present, but not detected, until it enters a region of high coverage under favorable observing conditions. That delay can look like waiting if interpreted loosely. In geometry, it is simply a change in detectability. The object's position relative to survey cadence, sky brightness, and background density changes until it crosses a threshold where it can be reliably flagged. As the geometric picture strengthens, the object's apparent motion is no longer just a drift on a detector. It becomes a set of line-of-sight vectors that are consistent with a three-dimensional path under gravity within uncertainties. The object can be predicted to appear in a specific region on a specific night. Recovery confirms the geometry. Failure to recover can indicate that the orbit is still uncertain, that the object is fainter than expected, or that some assumption is wrong. Each outcome feeds back into the geometric model. The goal is to reach a state where the object's sky position is predicted with narrow uncertainty, because only then do later claims about deviations become meaningful. A trajectory is not altered by rhetoric. It is altered in the physical sense only if measured positions depart from predictions in a way that survives uncertainty and survives the full stack of geometric corrections. In this region, the careful conversion from angles to a path lays the groundwork for that later test, while keeping the interpretation anchored in what geometry allows and what it does not. As the observation arc extends beyond the first nights, the data becomes suitable for an early orbit solution that is more than a rough guide, yet still far from final. The process of orbit fitting begins with a practical aim: produce a path that predicts where the object will be found next. The path is not drawn by hand. It is computed by solving for a set of parameters that best reconcile the measured directions with a dynamical model. In the early stage, the dynamical model is almost always gravity-dominated. The sun's pull is the main term, with planetary perturbations included at a level appropriate to the needed precision. The unknowns are the object's position and velocity at a chosen reference time, and from these the orbit can be expressed in standard elements that describe its size, shape, and orientation. The central point is that these elements are not measurements. They are a compact description of a computed state that matches the observations as well as possible within assumed uncertainties. The early orbit fit faces a constraint that shapes everything that follows. Distance is not directly observed. Each measurement is a direction. If the object lies closer along that direction, its real speed and curvature differ from the case where it lies farther. With a short arc, the fit can trade distance against velocity in ways that still match the angles. This trade is a form of degeneracy. It produces a family of plausible solutions rather than a single sharply determined orbit. In practice, the fitting algorithm searches for the solution that minimizes residuals, the differences between predicted and observed directions. Because the relationship between orbital parameters and observed angles is nonlinear, the algorithm iterates. It adjusts parameters, computes predicted positions at the observation times, compares them to the measured positions, and adjusts again until improvement stalls. A best fit is meaningful only when paired with an uncertainty description. That uncertainty is often represented by a covariance that encodes how uncertain each parameter is and how those uncertainties are correlated. In the early phase, correlations can be strong. A slight shift in distance can be compensated by a slight shift in velocity, and both shifts can be linked to small changes in the orbit's orientation. When the covariance is propagated forward, it becomes an uncertainty region on the sky for future dates. That region tells observers where to search. It also tells analysts how much confidence they should place in any apparent deviation. If the uncertainty region is large, a large change in predicted positions after adding new data is expected. Such changes are informational rather than physical. They reflect a narrowing of the family of plausible orbits. The quality of the early fit also depends on the data weights assigned. Not all astrometric points are equal. A bright, sharp detection under good seeing can yield a precise position. A faint detection near the noise floor can be less precise and can also be biased by noise. Observations taken at high air mass can carry refraction-related biases. Observations taken when the object is trailed can carry centroid biases depending on how the trail is modeled. The fitting process often assigns weights that reflect expected precision. If the weights are wrong, the fit can be pulled toward less reliable points. A robust analysis inspects residuals by observatory and by time. If one observatory's data show a consistent offset, that may indicate a systematic bias, and its weight may need adjustment. The aim is not to make the fit look pleasing. It is to reflect realistic uncertainties so that later conclusions are not built on underestimated error. In the early phase, orbit solutions can change in ways that sound dramatic if described loosely. A new night of data can shift the predicted perihelion distance, alter the implied orbital period, or change whether the orbit appears bound or nearly unbound. These shifts can occur because the initial arc might have been too short to constrain curvature, and curvature is what distinguishes a long-period ellipse from a near parabolic path. If the object is discovered when its apparent motion is slow, the curvature information accumulates slowly, and orbit parameters can remain uncertain longer. This can create the impression of an object that is not simply passing through, but lingering. In physical terms, it means the data provide less leverage per day, so the orbit remains more flexible and the uncertainty region shrinks more slowly. The object may also remain in a similar sky region if its relative motion projected onto the sky is low, and that too can give a sense of residence. Yet the orbit solution is still forming. It is not evidence of a stationary object. It is evidence of an observational geometry that is not yet constraining. The phrase "never passing through" can also be translated into specific orbital criteria. But those criteria belong to later stages when the orbit is better determined. Early on, the only safe statement is whether the object's motion is consistent with being gravitationally bound to the Sun within uncertainties, and what range of semi-major axes and eccentricities remain plausible. A bound orbit implies an ellipse and a return on some timescale. A nearly parabolic or hyperbolic solution implies a one-time passage. But in early fits, the uncertainty on eccentricity can be large. A solution may appear slightly above 1, implying hyperbolic, but that could be within uncertainty. A small systematic bias in early astrometry can also push eccentricity estimates. Analysts therefore avoid definitive language until the arc is long enough. They treat early orbit classification as provisional, and they allow for the possibility that the orbit will be revised. In addition to the uncertainty in orbital elements, there is uncertainty in what is being measured. If the object has a faint coma, the centroid may shift relative to the nucleus. If the object brightens due to dust release, the center of light can move. This can cause systematic residuals that the orbit-fitting algorithm might interpret as a need to adjust orbital parameters. In early stages, such effects can be mistaken for geometric curvature because both can shift measured positions. A careful analysis checks for signs of extended structure and for correlations between residuals and brightness. If residuals worsen as the object brightens and shows a coma, centroid bias becomes a concern. If residuals remain stable across brightness, changes centroid bias becomes less likely, though it cannot be ruled out without imaging. Early orbit fitting also includes the possibility of false linkages. In crowded data streams, it is possible for detections from different objects to be mistakenly associated as belonging to one track, especially if the detections are sparse. Such a linkage can produce an orbit that seems odd and later collapses when follow-up fails. Once more data arrive, the mislink can be identified and removed, producing a sudden jump in the orbit solution. From the outside, such a jump can look like a trajectory change. In reality, it is a correction in the data association. This is why independent confirmation and consistent recovery are crucial. A real object is recovered where predicted. A mislinked track is not. By the end of this early orbit phase, the object's path is still surrounded by uncertainty, but the uncertainty is now quantified and structured. Predictions exist, and recoveries refine them. The trajectory is not yet something that can be said to never pass through or to wait. It is a best fit under gravity to a growing set of angles and times with a well-defined uncertainty region that still allows revision. The disciplined posture remains to treat changes in the orbit solution as changes in knowledge unless and until the orbit is tight enough that persistent residuals appear. Only when the residuals become smaller than the claimed effect does it become meaningful to discuss whether an additional acceleration exists. Until then, the early orbit fit is an act of careful restraint. It keeps the object in hand. It maps what is known and what remains uncertain, and it prevents the human urge for narrative from outrunning the geometry and the data. As additional nights of data accumulate, the orbit solution enters a more stable regime where the observation arc becomes long enough to tighten distance, curvature, and prediction in a way that can be tested rather than merely updated. The change from early fitting to refined tracking is not a single threshold. It is a gradual shift in leverage. Over time, Earth's changing position provides a wider baseline, and the object's own motion reveals more of its path. Predictions begin to hold. The uncertainty region on the sky for the next observation night becomes smaller, and the object is recovered closer to the predicted center, rather than merely within a broad search zone. This is the stage where claims about lingering residence or apparent waiting can be translated into specific observational facts, such as a low apparent angular speed, a slow change in elongation from the sun, or a track that remains in a certain sky region because of geometry. Refined tracking improves the astrometry itself. Follow-up observations are often tailored for the target, If the object is moving quickly, observers can adjust exposure times to avoid trailing, or they can track at the object's rate to keep the object sharp at the expense of star trails. If the object is faint, they can take multiple short exposures and stack them in the object's frame to increase signal while controlling smear. Each method has trade-offs. Tracking at the object's rate complicates the use of star centroids as references because the stars are trailed. Stacking can introduce biases if the assumed motion used for stacking is slightly wrong. The refined stage, therefore, often includes careful choices about which exposures are used for astrometry and how the centroid is computed. The aim is to produce a consistent set of positions with well-understood errors. The diversity of observing stations also becomes a strength here. When multiple observatories contribute astrometry, the orbit solution becomes less vulnerable to a single instrument's systematic bias. Differences in detectors, optics, and reduction pipelines can reveal hidden issues. If one station consistently reports positions that sit offset from others, that pattern can be detected and handled by adjusting weights or by applying debiasing methods. If all stations agree, confidence increases that the measured positions reflect a true sky direction rather than a pipeline artifact. Observations from different latitudes and longitudes also enhance parallax leverage tightening distance estimates. Over weeks, the object moves into different star fields, reducing the risk that a local catalog distortion dominates the solution. These are quiet improvements, but they are exactly what turns a tentative orbit into a stable trajectory in the computational sense. Photometry. The measurement of brightness becomes more informative as well. A stable light curve can reveal a rotation period. Changes in the light curve can indicate tumbling or evolving surface activity. A general trend in brightness can indicate changing distance and phase angle and possibly activity. In refined tracking, analysts compare photometric behavior with astrometric residuals. If the object brightens and residuals increase or shift in a consistent direction, it suggests that the center of light may be changing, perhaps due to coma development or tail asymmetry. If the object's appearance remains point-like and brightness changes follow geometric expectations, centroid bias becomes less likely. This cross-check helps decide whether the astrometry traces the nucleus reliably. At this stage, the orbit model itself is often refined. Planetary perturbations are handled with precise ephemerides. Light time and aberration corrections are applied consistently. If the desired precision is high relativistic corrections for light propagation and gravitational dynamics near the Sun are included. These corrections are small, but their inclusion ensures that any remaining residuals are not the result of omitted standard terms. The refined model thus becomes a baseline against which deviations can be judged. Without such a baseline, the later claim that an object does not pass through cannot be anchored. With it, the orbit can be projected reliably enough to test whether the object follows the projection. The perception of an object that is waiting can arise in several refined tracking scenarios that are physically ordinary. One is a low relative velocity geometry. If the object's motion projected onto the sky is small, it can appear to drift slowly and remain in a similar area for a long time. Another is a geometry where the object remains at a relatively stable elongation from the Sun, keeping it in the observable night sky without rapidly diving into the sunlit glare. Another is a trajectory that keeps the object at roughly similar distance for a time, such as near aphelion, in an elongated orbit where motion is slow. Yet these interpretations depend on the orbit, and the orbit depends on data. Refined tracking provides the data needed to distinguish among these cases. A key feature of this stage is prediction testing. The orbit solution is used to predict the object's position at times not yet observed. When the object is observed at those times, its measured position can be compared to the prediction. The comparison yields residuals. If residuals behave like random noise at the level expected from measurement errors, the model is adequate. If residuals show a systematic drift, the model is missing something. In refined tracking, the systematic drift becomes harder to dismiss as uncertainty in the orbit, because the orbit is now tight. This is the point where an additional acceleration term may be considered, but the decision is not automatic. First, analysts check whether the drift is associated with particular observing conditions, such as high air mass or particular instruments. They check for catalog-related effects by examining whether residuals change with sky region. They check whether residuals correlate with brightness or with morphological changes. The refined stage is as much about rejecting artifacts as it is about detecting forces. Another practical aspect is that refined tracking can reveal whether earlier data points were biased. When the orbit becomes tight, earlier points can be re-evaluated. If early survey detections consistently sit offset in a particular direction relative to the refined orbit, it may indicate a systematic bias in early measurements, perhaps due to lower signal-to-noise or due to a reduction pipeline assumption. Analysts may then downweight those early points or apply corrections. This can produce a small shift in the orbit, but the shift is a correction of the data's influence, not a physical change. It also highlights why early dramatic interpretations are risky. What looks like a change in the object's behavior can simply be a change in the weight assigned to noisy early points. By the end of this refined tracking stage, the object's trajectory in the operational sense becomes something that can be trusted to guide telescopes night after night. The orbit does not cease to be updated, but updates become incremental. The uncertainty region shrinks. The object is recovered reliably. Residuals become the main diagnostic rather than orbital element swings. If the object appears to linger, that lingering can be measured as a slow change in its sky coordinates and as a slow change in its geometric relationship to Earth and Sun, rather than as a narrative claim. If the object's motion shows persistent offsets from prediction, those offsets can be quantified and tested for cause. The refined stage thus completes the transition from discovery and provisional orbit fitting to a stable predictive framework within which any claim that the object is not passing through can be evaluated as a measurable statement about whether its motion is consistent with gravity alone, or whether additional forces or biases must be considered. The phrase "never passing through" sounds decisive, but in careful work, it can only be understood by translating it into measurable criteria. Passing through in an orbital sense usually refers to an object that arrives from far away, crosses the inner region of the solar system, and then departs on a path that will not return on a human timescale, or perhaps not return at all if the orbit is unbound. Never passing through could therefore mean that the orbit is bound, and that the object is expected to return, implying an ellipse rather than a one-time flyby. It could also mean something subtler, that within the window of observation, the object's motion is slow enough, or the geometry is such that it spends an unusually long time in a region where surveys can keep seeing it, creating the impression of residence. It could mean that the orbit, when refined, places the object not on a sweeping crossing track, but on a path with a long dwell near a turning point, such as aphelion, where orbital speed is naturally low. Each of these interpretations is ordinary physics, but they require different evidence, and the evidence must come from the orbit solution and its uncertainties rather than from the emotional weight of the phrase. A first measurable criterion concerns orbital binding. An object that is truly passing through on a one-time path will typically have an eccentricity that is at least very near 1, and if it is unbound, it exceeds 1. Yet early estimates of eccentricity can be biased by short arcs and by subtle systematics. A refined orbit that includes many observations across a broad baseline can determine eccentricity with enough precision to distinguish bound from unbound in many cases. If the orbit remains consistent with a bound ellipse within uncertainty, then never passing through can be translated to a simple statement: the object is gravitationally bound to the Sun and will return on some period. If the period is extremely long, it may still be effectively one time in practice, but the binding remains a physical distinction. If the orbit is confidently hyperbolic beyond uncertainties, then the object is passing through in the strict sense, and the phrase would be incompatible with the measurements. This first criterion therefore depends on whether the refined solution decisively classifies the orbit. A second criterion concerns residence time in the observable region. Even a passing object can appear to linger if its apparent motion is slow and if it remains in night sky regions that are well covered by surveys. Apparent motion is an angular speed on the sky, and it depends on distance and relative velocity. If the object is distant, its parallax is small, and its apparent motion can be slow. If its velocity relative to Earth projected onto the sky is small, it can drift gradually and remain in similar star fields for many nights. Residence in this sense is a statement about observing geometry. It can be quantified by tracking how quickly right ascension and declination change per day, and how those rates evolve. It can also be quantified by how long the object remains at a safe elongation from the Sun, meaning far enough from the Sun's glare to be observed at night. An object that spends many weeks in such conditions will feel present, but the presence is simply the result of relative motion and visibility windows. A third criterion concerns the object's motion relative to the Sun at the scale of its orbit segment. In orbital mechanics, speed is not constant. An object moves faster near perihelion and slower near aphelion. If the observed interval happens to coincide with a portion of the orbit where radial distance changes slowly, then the object's geometry and brightness may change slowly as well. This can look like weighting. It can be quantified by the rate of change of heliocentric distance over time in the orbit solution. A small rate indicates a near turning region or a geometry where motion is largely transverse rather than radial. If the object is near aphelion, the slow speed is expected. If it is near perihelion, slow radial change would be unusual and would prompt checks of the fitted orbit, because near perihelion, the speed and the change of geometry often accelerate. A fourth criterion concerns whether the object's trajectory is stable in prediction. An object that is passing through but is well modeled by gravity will still follow predictions closely once the orbit is constrained. The predictions will change only slightly as new data arrive. In this case, the object is not doing anything exceptional. It is simply on a path. By contrast, if repeated predictions systematically miss in the same direction beyond realistic uncertainties, then an additional acceleration may be present, or a measurement bias may persist. That is not the same as never passing through, but it is sometimes conflated with it. A persistent residual drift can create the impression that the object is resisting the expected path, that it is not simply passing along a computed curve. The measurable version of that impression is a residual pattern, an offset between observed and predicted positions that accumulates over time under a gravity-only model. This is where language must stay clean. A changing orbit solution is not evidence that the object changes its path. It is evidence that knowledge changes. A persistent residual pattern after the orbit is tight is evidence that the model is missing something, or that the data carry a bias. The measurable question becomes whether a gravity-only model built with complete planetary perturbations and correct geometric corrections can fit the observations within uncertainties. If it cannot, the next measurable question is whether adding a non-gravitational term reduces residuals and improves forward prediction. If it does, then the object's motion includes an additional acceleration that can be parameterized. That acceleration may be due to outgassing radiation pressure, thermal recoil, or centroid bias. None of these mechanisms implies weighting. They imply that the object is not a perfect test mass, or that the measurements do not perfectly trace the center of mass. The phrase "never passing through" can also be misused to imply that the object has no net progression, as if it is stationary in space. In orbital terms, stationarity is not a typical property of small bodies relative to the Sun. Even objects near a stable gravitational configuration still move. There are special regions, such as certain co-orbital configurations, where objects can share an orbit with a planet and appear to linger near certain points relative to that planet. Yet for a newly found object with an uncertain orbit, such interpretations require strong evidence. The measurable test would be whether the object's orbit is near resonant or co-orbital relationships, and whether its relative motion to a planet remains bounded in a way consistent with such dynamics. Establishing that requires an accurately determined orbit and a dynamical analysis over time, because resonance and co-orbital behavior are properties of long-term motion, not just a short observational arc. Without that, the safest translation of lingering remains simple geometry and visibility. In addition, the observing network itself can create the illusion of residence. Once an object is designated and tracked, it is deliberately observed more often than random sky points. The data set becomes dense. This can make the object feel continuously present in reports and updates, even if its motion is ordinary. The measurable counterpart is cadence, how often it is observed, and by whom. A dense cadence is an observing choice, not an orbital property. Therefore, any statement that the object is not passing through must avoid confusing attention with dynamics. The orbit decides dynamics, and the orbit is inferred from measurements, not from how often those measurements are discussed. By the end of this region, never passing through becomes a set of specific questions that can be answered with data. Is the orbit bound or unbound, and with what confidence? How slow is the apparent motion, and is that slowness due to distance relative velocity or geometry near a turning point? How long does the object remain at observable elongations and in survey-covered sky regions? Do residuals under a gravity-only model remain random, or do they drift systematically? If a drift exists, does it correlate with activity indicators or with observing conditions? These questions do not add drama, they remove it. They turn a suggestive phrase into a small number of testable statements. With those statements in hand, the next inward step can establish the gravitational baseline in a fully specified way, and then examine whether any persistent offsets remain that might require non-gravitational forces or a refined understanding of what the astrometry is truly measuring. A claim that an object is not passing through must be anchored to a gravitational baseline, because gravity provides the most reliable and least flexible prediction for how a small body should move when no other forces are significant. The baseline begins with a chosen reference time at which the object has a position and velocity in an inertial frame. From that state, the object's path is integrated forward and backward under the gravitational influence of the Sun and the planets. The integration is not a vague idea. It is a stepwise calculation that repeatedly evaluates gravitational accelerations based on changing distances and updates the object's position and velocity accordingly. The result is a predicted trajectory in space that can be converted into predicted sky positions as seen from Earth at each observation time. The Sun dominates the gravitational field for most small bodies, but the planets matter because their tugs can shift a predicted position by an amount that becomes measurable when astrometry is precise. A comprehensive baseline therefore uses precise planetary ephemerides, meaning well-tested tables or models that provide the positions and velocities of planets across time. These ephemerides are built from decades of tracking data, and their role here is to ensure that the model reflects where the planets actually are when they tug on the object. The object's motion is then computed under the combined acceleration from the Sun and planets. The gravitational terms vary smoothly with distance, and if the object passes near a planet, the gravitational influence can produce a stronger deflection. Such deflections are not anomalies. They are the predictable consequences of close approaches. The baseline's purpose is to include them so that what remains is not mistaken for something else. A correct baseline also accounts for how observations are made. Observations are taken from Earth's surface, not from Earth's center, and Earth is moving. For each observation time, the observer's location must be computed in the same inertial frame used for the orbit integration. This requires transforming from Earth-fixed coordinates to inertial coordinates using Earth rotation and orientation parameters. It also requires accurate time standards. A small timing error can translate into a small error in observer position and in the predicted line of sight. In high-precision work, these details matter because they can produce systematic residuals that look like a real dynamical effect. The baseline, therefore, is as much about reference frames and timing as it is about gravity. Once the object's predicted position in space is available for an observation time, it must be turned into a predicted direction on the sky. This conversion includes light travel time. light takes time to travel from the object to Earth. The predicted direction at observation time must therefore correspond to the object's position at the time the light left it, not at the time the light arrives. This correction is computed by iterating because the light travel time depends on distance, which depends on the object's position. The baseline also includes aberration, the apparent shift in direction due to Earth's motion. For the level of precision required to discuss subtle residual patterns, these corrections are standard. They remove small known effects so that residuals are not inflated by omissions. The gravitational baseline can also include small relativistic corrections when appropriate. In the vicinity of massive bodies, space-time curvature alters the motion slightly and alters the propagation of light. These effects are well tested and become relevant when astrometry is extremely precise or when geometry places the object close to the sun in the sky. The inclusion of such corrections is not a dramatic escalation. It is part of a thorough baseline. The goal is not to add complexity for its own sake. The goal is to prevent the later introduction of non-gravitational forces from compensating for missing known terms. After all this, the baseline is judged by residuals. For each observation, the predicted sky position is compared to the measured one, and the difference is recorded as a residual. If residuals are random and consistent with measurement uncertainty, the baseline is adequate. If residuals show systematic patterns, the baseline is incomplete in some sense. Yet incomplete can mean two things. It can mean the gravitational model is missing a mass term or has a computational error. Or it can mean that the object experiences non-gravitational accelerations, or that the observations are biased by the object's appearance. The baseline is designed to rule out the first category as far as practical, so that attention can move inward to the second category only when justified. An object that is described as waiting can produce a particular kind of residual confusion. If the object's apparent motion is slow, measurement errors can become relatively more important because small timing or centroid biases can produce residuals comparable to the motion itself over short intervals. In such cases, it can take longer for the orbit to become tight and for the baseline to predict positions with narrow uncertainty. Analysts then must be cautious not to interpret ordinary baseline settling as a persistent anomaly. The test is whether residual drift persists after the orbit is already tight. If the orbit remains uncertain, changes in predicted positions are expected and cannot support a claim of behavior beyond physics. Another potential source of confusion is the interplay between survey data and follow-up data. Survey measurements may have one set of systematics, while follow-up measurements have another. If the baseline orbit is fit using both residual patterns, can reflect the offset between systems, rather than the object's true motion. Analysts therefore examine residuals by observatory. If one system is consistently offset, they may apply debiasing or adjust weights. A baseline fit that treats heterogeneous data as if they were homogeneous can create the illusion of a non-gravitational effect. The baseline is therefore not only about integrating gravity. It is also about ensuring that the data set is treated realistically so that residual patterns reflect the sky rather than the differences between pipelines. Once a baseline is secure, it can be used to test specific interpretations of never passing through. If the orbit is bound baseline integration forward and backward, shows whether the object returns and on what timescale. If the orbit is unbound, baseline integration shows that it departs and does not return under gravity alone. If the object appears to linger in a region, the baseline reveals whether it is near a turning point or whether the lingering is observational tied to Earth relative geometry. The baseline can compute the object's heliocentric distance over time, its rate of change, and its predicted sky path. These are measurable outputs that can replace ambiguous language. Crucially, the baseline also sets the stage for evaluating whether an additional acceleration exists. If residuals drift in a consistent direction over time, analysts can estimate what small acceleration would be needed to reduce that drift. They can test whether adding such an acceleration improves fit and prediction. But they only do this after the baseline is as clean as practical. Otherwise, the added acceleration might simply be compensating for an omitted correction or a catalog bias. The baseline is therefore a gatekeeper. It separates the ordinary complexity of precise orbit prediction from the possibility that the object is experiencing small forces beyond gravity, or that the measured positions are influenced by evolving light distribution. In this region, the discipline is to treat gravity as the reference language of motion and to treat departures from gravitational prediction as quantitative differences that must be explained either by improved modeling, improved measurement, or additional forces. The phrase "never passing through" then becomes measurable as orbital binding and residence time in certain geometries, while the phrase "waiting" becomes measurable as low relative velocity or slow change in heliocentric distance. If the baseline shows ordinary motion consistent with gravity and uncertainties, then the phrase is an interpretive flourish. If the baseline shows persistent residuals beyond uncertainty, then the phrase points not to intention, but to a missing term. And the next inward region is where those residual patterns are examined in detail to see whether they indicate outgassing light pressure, thermal recoil, or an observational bias tied to dust and coma. With a gravitational baseline in place, the question becomes not whether the object feels unusual, but whether the data leave a structured remainder once the baseline is subtracted. That remainder is the residual field, a record of how observed positions differ from predicted positions at each observation time. Residuals are small angles on the sky, but their patterns can be meaningful. The first diagnostic is whether residuals behave like noise. Noise has no memory. It scatters around zero and does not drift systematically with time. When residuals do drift, it suggests either a persistent measurement bias or a missing acceleration in the model. When residuals cluster by observatory, it suggests systematics in that observatory's data. When residuals correlate with geometry such as altitude above the horizon or sky region, it suggests atmospheric or catalog-related biases. This region is where a narrative phrase like "waiting" is either translated into a residual pattern with measurable structure or dissolves into the ordinary scatter of measurement uncertainty. Residuals are typically examined in two sky directions, so that both magnitude and direction are known. A drift might appear predominantly in one direction, which can be informative. If the drift aligns with the object's direction of apparent motion, timing errors or along-track accelerations become candidates. If the drift aligns with the sun-object direction projected on the sky, radiation pressure or outgassing becomes candidates. If the drift aligns with the zenith direction for a given observatory, refraction errors become candidates. These alignments are not proofs, but they guide testing. In careful analysis, residuals are plotted as a function of time of phase angle of heliocentric distance of air mass and of observatory. The purpose is to see whether the pattern is stable across contexts, or whether it is tied to a specific subset of conditions. A key distinction is between residuals that diminish as more data are added and residuals that persist or grow. Residuals can appear large early on simply because the orbit is not yet tight. As the orbit tightens, those residuals should shrink. If they do not, and if the orbit is already constrained, then the residuals carry real information. Persistence is therefore evaluated relative to the evolving uncertainty. If the uncertainty ellipse at a given time is still large, a residual is less significant. If the uncertainty ellipse is small and residuals remain systematically offset, significance increases. This is why claims of unusual behavior cannot be made responsibly without reference to uncertainties. Residuals can also be influenced by the object's brightness and morphology. If the object is faint, centroid estimates can be noisy and biased. If the object is active, the center of light can shift relative to the nucleus, producing residuals that mimic a dynamical effect. Analysts therefore look for correlations between residuals and photometry. If residuals drift more when the object brightens or when it shows a developing coma, the measured positions may be tracing the evolving coma rather than the nucleus. If residuals remain stable across brightness changes and the object appears point-like, then the residuals are more likely to reflect dynamics rather than morphology. This correlation test is not always decisive, but it is a critical piece of the puzzle. Another important aspect is the source of reference stars. If the object moves into a sky region where catalog systematics differ, residuals can shift. The shift can look like an abrupt change, a step, rather than a smooth drift. If the step coincides with a change in star field, it suggests a catalog bias. If it coincides with a change in observatory or in reduction pipeline, it suggests a pipeline bias. If it coincides with a photometric outburst and morphological change, it suggests an activity-related centroid change. If it coincides with none of these and persists across many observatories, it becomes more likely to reflect a real acceleration. When residuals point toward a missing acceleration, analysts can estimate its direction and magnitude. A small constant acceleration would cause residuals to drift in a predictable way over time. A distance-dependent acceleration would cause the drift rate to change as the object approaches or recedes from the sun. An acceleration tied to solar direction would remain roughly radial. An acceleration tied to rotation and thermal effects might have transverse components. The residual pattern can be used to fit a parameterized acceleration model. This fitting is done carefully because adding parameters can always improve a fit in a narrow sense. The true test is whether the model improves forward prediction and whether it reduces residuals across independent data sets. The phrase weighting, if translated into residual behavior, might correspond to an object that remains consistently offset from predicted positions in a way that makes it seem to resist the baseline trajectory, as if it is not simply passing along. The measurable version of that would be residuals that drift in a consistent way even when the orbit is tight. Yet even then the cause would not be weighting. The cause would be an acceleration or a bias. If the acceleration is real, it is likely due to outgassing radiation pressure or thermal recoil. If the bias is observational, it is likely due to coma asymmetry or reduction systematics. The residual pattern therefore decides whether the phrase has any measurable content. Residual analysis also includes robustness checks that try to break the pattern. Analysts may refit the orbit using only the highest quality data subset. They may exclude high air mass observations or data from a particular telescope or points taken when the object was near a crowded star field. If the residual pattern persists under these restrictions, it becomes harder to attribute it to a specific observational bias. They may also reduce images using a different star catalog or a different reduction pipeline. If the pattern changes, it points to reduction issues. If it remains, it points back to the object's motion or to a bias common across pipelines, such as a shared catalog systematic. The interpretation of residuals must also respect the cadence of observation. A sudden change in residuals might suggest a sudden change in acceleration or a sudden change in measured centroid. But if the observations are sparse around the suspected change, the apparent suddenness may be an artifact of sampling. In reality, the change could be gradual but unobserved. To resolve this, denser observations are needed, or at least observations targeted, around times when the object is expected to show changes, such as near perihelion, if activity is expected to rise. A careful residual analysis therefore informs observing strategy. It suggests when and how to observe, to discriminate between smooth, distance-dependent forces and episodic events. At the end of this region, the outcome is not a story. It is a classification of residual behavior. Residuals may be consistent with noise, in which case the baseline is adequate, and the impression of weighting is not supported by dynamics. Residuals may cluster by observatory, in which case systematics dominate, and the analysis must return to calibration. Residuals may correlate with brightness and morphology, in which case the measurement target is shifting and nucleus-centered astrometry is needed. Or residuals may persist across instruments with a coherent direction and time dependence, in which case an additional acceleration term is warranted, and the next inward step is to examine the observational chain for vulnerabilities that could mimic such a term, and then to test specific non-gravitational mechanisms. Only after this classification can the phrase "never passing through" be discussed with clarity, because the object's motion either follows gravity within uncertainty or it requires additional known forces. In neither case does the data demand intention. It demands a model that matches measured angles and times, and residual analysis is where that demand is expressed most plainly. Before moving inward to physical mechanisms, the residual pattern must be tested against the many ways measurement can create a coherent illusion. The measurement chain begins with photons and ends with catalog-referenced coordinates, and each step can imprint a bias that persists across nights. If the object is faint, these biases can become comparable to the claimed deviation. The first vulnerability is the detector. Each pixel responds slightly differently to light, and calibration frames correct these differences, but not perfectly. A small flat field error can shift the measured centroid of a faint point, depending on where it lands on the chip. As the object moves across the field of view from night to night, such position-dependent shifts can create a smooth residual drift that looks like an acceleration. This is especially plausible in wide-field survey cameras, where distortions and illumination gradients can be complex. A careful audit therefore asks whether residuals correlate with detector coordinates. If they do, the pattern is likely instrumental rather than dynamical. Optics introduce a related vulnerability. A telescope's field is not perfectly distortion-free. The mapping from pixel coordinates to sky coordinates is solved using reference stars, but the distortion model may not capture all subtle flexure or temperature-dependent changes. If the distortion changes as the telescope points to different altitudes or different azimuths, the astrometric solution can shift systematically. For a target observed at similar hour angles night after night, a repeatable pattern can appear. If the object's track keeps it in the same observing window, such as near dawn or near dusk, it can be observed under similar telescope orientations each night. This can reinforce a systematic effect and create the impression of stable, persistent residuals. A robust check is to compare observations taken at different hour angles or by different telescopes with different optical designs. If the anomaly is tied to one system, it is likely optical and reduction related. Timing is another high leverage point. The recorded time must represent the effective midpoint of exposure. If the reported time is systematically early or late by even a small fraction, a fast-moving object will appear displaced along its direction of motion. For an object with slow apparent motion, the effect is smaller, but a slow mover is often faint and therefore more vulnerable to centroid biases, so timing can still matter in combination. Timing errors can also be subtle if they vary with instrument configuration, such as different readout modes or different software versions. Analysts test timing by comparing residual direction to the known apparent motion direction and by checking whether the magnitude of residuals scales with apparent motion rate across different nights. A strong scaling suggests timing rather than acceleration. If multiple observatories contribute and only one shows the scaling, the problem is localized. Atmospheric refraction remains a quiet but persistent source of bias, especially when observations are taken at lower altitudes. Standard refraction corrections assume typical conditions, but pressure and temperature vary. More subtle is differential chromatic refraction, where the atmosphere refracts blue and red light differently. Reference stars have a range of colors, and the moving object may have a different color distribution, especially if it is dusty or has gas emission. At high air mass, a small color-dependent shift can occur between the object's centroid and the reference frame defined by the average of reference stars. If the object is observed repeatedly at similar air mass, the bias can be stable and can look like a persistent residual. A test is to compare residuals from observations taken at different air masses or in different filters. If residual direction and magnitude change with filter or air mass, atmospheric chromatic effects become likely. Reference catalogs can introduce their own stable biases. Catalog star positions are precise but not perfect, and their errors are not always random on small scales. There can be local distortions and small systematic offsets. If the object moves through different regions of the sky, it moves through different catalog error regimes. A step change in residuals can occur when the object enters a region with a different catalog bias. This can be misread as a sudden change in the object's trajectory. Analysts test this by re-reducing astrometry, using different catalogs when possible, or by comparing the object's residual behavior to that of other objects measured in the same fields. If multiple objects show similar residual offsets in that region, the bias is likely catalog-related. Reduction pipelines also make choices about how to measure the object. The point spread function model used for centroiding may assume symmetry. If the true point spread function is asymmetric, perhaps due to tracking or wind, the centroid can be biased. For faint objects, noise interacts with the model and can pull the centroid. Trailing introduces another complexity. If the object trails, the centroid depends on how the trail is modeled. If the trail is treated as a point, the centroid can shift. If the trail is treated as a line, the fit may depend on background subtraction. Different pipelines handle these differently. A pattern that appears in one pipeline but not in another is a strong indicator of reduction artifacts. Blending with background sources is a common and underappreciated pitfall. The object can pass near a faint background star or galaxy. If the object overlaps the background source, the combined light distribution shifts, biasing the centroid. In a single image, this may not be obvious. Over several nights in a crowded field, repeated blending can occur. The result can be a cluster of residuals that pull the orbit. If those points are not identified and down-weighted, the fit can develop a spurious acceleration. Analysts check for blending by examining image cutouts and by cross-matching the object's track with catalogs of background sources. They also look for outlier residuals that coincide with crowded fields. The object's own light distribution can be the most deceptive vulnerability when the object is active. A faint coma or a short dust tail can shift the center of light relative to the nucleus. If the tail points away from the sun, the centroid can be displaced anti-sunward. If the strength of the tail changes with time, the displacement changes. This can mimic a distance-dependent acceleration away from the sun, which can be mistaken for radiation pressure or outgassing. The key diagnostic is whether the measured position depends on aperture size. If a larger aperture includes more tail light and shifts the centroid, then extended structure is influencing the measurement. Another diagnostic is whether high-resolution images show asymmetry that aligns with residual direction. If they do, centroid bias is likely. A careful audit in this region uses robustness as its standard. The question is not whether any one vulnerability could exist in principle, but whether the anomaly survives tests designed to reveal such vulnerabilities. Analysts may restrict the data set to the highest signal-to-noise observations. They may exclude observations at high air mass. They may exclude survey points with known larger systematics. They may separate data by instrument and compare fits. They may try different centroiding methods and see whether results change. If the anomaly disappears under these tests, the path inward toward physical forces is blocked because the signal was not robust. If the anomaly persists, especially across independent instruments and independent reductions, then the possibility of a real non-gravitational acceleration becomes stronger. In the context of a phrase like "it was waiting," this audit is essential because a persistent, slow residual drift can be created by stable biases as easily as by real forces. A stable bias can make the object appear consistently offset from prediction giving an impression of resistance or non-compliance with the expected track. Yet in a purely mechanical sense, the object is either on the predicted path under the correct model and correct measurements, or it is not. The audit aims to ensure that the measurements are indeed tracing a single physical point and that the reference frame is stable. Only then can the next inward step consider non-gravitational forces as real dynamical contributors rather than as placeholders for the imperfections of observation. In this way, the measurement chain is treated as part of the physical environment because it shapes what is seen and therefore shapes what must be explained. If the residual pattern remains after the measurement chain is stress-tested, the next inward step considers the standard non-gravitational mechanisms that can make a small body's motion depart from a gravity-only baseline beginning with outgassing. Outgassing is not a metaphor. It is a transfer of momentum. When volatile material in or near the surface warms enough to sublimate, gas escapes into space. The escaping gas carries momentum away. Conservation of momentum requires the nucleus to receive an equal and opposite push. The push can be small, but if it acts continuously over weeks or months, it can accumulate into a measurable shift in predicted sky position. This is one of the most common reasons comet trajectories deviate from purely gravitational predictions, and it is considered even for objects whose activity is faint, because thrust depends on directionality and production rate, not on how visually dramatic a coma appears. Outgassing depends on solar heating, but the dependence is not a simple on-off switch. Different volatiles sublimate at different temperatures. Far from the sun, water ice remains largely stable, but more volatile substances can sublimate and drive activity. Closer in water, ice can dominate. The surface is not uniform, so activity can be localized. A dust mantle can insulate underlying ice, delaying activity until heat penetrates. Cracks and vents can channel gas into jets. Each of these factors influences not only how much gas is produced, but where it leaves and in what direction it pushes. A uniform isotropic release would produce little net thrust because forces cancel. A localized jet produces a net thrust that can be significant relative to its gas production. The direction of thrust is central. In the simplest picture, the sun warms the sunward side and thrust points roughly away from the sun, but real objects complicate this. Thermal inertia creates a lag. The warmest region may occur after local noon on the rotating body, shifting the main gas emission region away from the direct sun line. The thrust direction can then be rotated relative to the radial direction. If the object rotates steadily, the time-averaged thrust can be stable and can be approximated by a fixed set of components in an orbital frame. If the object tumbles, the thrust direction in space can vary, and the average can change over time. If activity turns on and off, thrust can be episodic. These behaviors can produce residual patterns that do not match simple distance-dependent models. To connect outgassing to the orbit, analysts introduce non-gravitational acceleration terms into the integration. These terms are often expressed in components aligned with directions tied to the orbit, such as toward the sun along the velocity and perpendicular to the orbital plane. The acceleration magnitude is scaled by a function that increases as the object approaches the sun, reflecting increased sublimation. The parameters are then fitted to reduce residuals. A successful fit does not prove the physical cause on its own, but it shows that the residual pattern behaves like a continuous thrust rather than like noise. The strongest test is prediction. If the fitted thrust term improves the ability to predict future positions, it is likely capturing a real dynamical effect. Outgassing also has observable consequences in appearance and brightness. Gas and dust create a coma, and dust can create a tail. Activity can cause a gradual brightening as the object approaches the sun, and an asymmetry in brightening before and after perihelion can occur because of thermal lag and surface evolution. Spectroscopy can detect emission from gas species or from fragments created by sunlight breaking molecules apart. Yet these signs are not guaranteed. Some objects can have low dust content producing weak visible coma even when gas is present. Some objects can produce thrust from a small active area that is difficult to detect if the overall gas production is low. Conversely, a bright dust coma can exist, while net thrust is modest if activity is distributed. Therefore, the absence of a dramatic coma does not rule out outgassing thrust, but it does shift the burden toward careful constraints and consistency checks. The relationship between outgassing and residuals is complicated by centroid bias. A jet that produces thrust also produces asymmetric brightness. The asymmetry can shift the center of light. The measured astrometric position then includes a bias that is aligned with the jet direction or tail direction. This bias can mimic a dynamical acceleration. In some cases, it can even cancel part of the dynamical signal or amplify it depending on geometry. Therefore, a non-gravitational fit that reduces residuals could be partially compensating for centroid biases rather than for true center of mass acceleration. Analysts attempt to disentangle this by using observations that minimize coma influence, by comparing different apertures, and by examining high-resolution images for nucleus position relative to coma. If residuals change when the astrometric method changes, centroid bias is implicated. Outgassing can also be episodic in a way that aligns with the tidal language of weighting. An object could appear quiet and then show a burst of activity changing both its brightness and its motion. Yet in physics terms, weighting is simply low activity or low detectability, followed by a change in surface conditions. A sudden exposure of fresh ice, perhaps by a crack opening or a small collapse, can increase gas production. An outburst can produce a transient acceleration and a transient shift in centroid. If observations are sparse during the transition, the orbit fit may interpret the change as a smooth acceleration, even if the true force history is more complex. This is why dense monitoring around suspected activity changes is valuable. If outgassing is the driver, the implied acceleration should have a sensible direction and magnitude relative to plausible gas production rates. The thrust required to produce a certain acceleration depends on mass, and mass depends on size and density. Size estimates from brightness are uncertain without albedo constraints, and activity complicates this further because dust can dominate brightness. Therefore, analysts often treat size and density as ranges rather than fixed values. They then ask whether plausible combinations yield a gas production rate that is consistent with observational limits from spectroscopy and with the observed brightness and coma. If the required production is far above limits, outgassing becomes less likely as the dominant cause. If it is within limits, it remains plausible. This evaluation does not demand perfect knowledge. it demands consistency. Outgassing models also allow for asymmetry around perihelion. Many comets show stronger activity after perihelion because heat penetrates and peaks later. If residuals show a similar asymmetry, it supports an outgassing interpretation. If residuals show the opposite, it may still be possible depending on surface conditions and rotation, but the interpretation becomes more constrained. If residuals do not follow solar distance in any clear way, outgassing may still be present but not dominant, or the data may be dominated by other effects. In the context of a claim that the object was never passing through, outgassing thrust does not change whether the object is bound or unbound in a dramatic way over short spans, but it can shift the fitted orbital elements enough to affect classification near the boundary. A small non-gravitational acceleration can bias eccentricity estimates. This is an important point, because an object that seems unbound under a gravity-only fit could become consistent with bound motion when non-gravitational terms are included, or vice versa, depending on the direction of thrust and the geometry of observation. This does not mean the object changes its fundamental nature in response to classification. It means the classification depends on the assumed force model. Therefore, when dramatic claims are made about never passing through it, becomes essential to state which model is used and how sensitive the classification is to plausible non-gravitational accelerations. Outgassing thus serves as a grounded candidate mechanism that can produce measured deviations and can influence how the object's larger trajectory is interpreted. It is not an exotic explanation. It is part of the known behavior of small bodies. The challenge is not to invoke it casually, but to test whether the residual pattern, the object's appearance, and the plausible physical parameters form a consistent picture. If they do, the motion is explained within established physics. If they do not, attention shifts to other non-gravitational mechanisms, such as radiation pressure and thermal recoil, and to the possibility that what is being measured is not the nucleus at all. In all cases, the path inward remains guided by the structure of residuals and by the demand that any proposed mechanism improve prediction and survive cross-instrument scrutiny. Beyond outgassing, sunlight itself becomes both a force and a source of confusion because it can push on matter directly, and it can also shape the dust environment that determines what the telescope measures. Sunlight carries momentum. When photons strike a surface and are absorbed or reflected, they transfer momentum, producing a pressure. For a large body, this pressure is usually tiny compared to the sun's gravity. For a very small body, or a body with unusually low mass for its area, the acceleration can become measurable. The critical quantity is area relative to mass. If the object presents a large cross-section while having little mass, the radiation pressure acceleration rises. This is why radiation pressure is considered for small fragments, porous bodies, or objects whose size is uncertain because brightness is contaminated by dust. Direct radiation pressure produces an acceleration that is primarily away from the sun. The magnitude decreases with the square of heliocentric distance because sunlight intensity falls with distance. In orbit, fitting a radial acceleration of this form can mimic certain outgassing components, particularly if outgassing thrust is also roughly anti-sunward. Distinguishing them requires additional information. If the object shows no signs of gas or dust radiation pressure, becomes more plausible. If the object shows activity, outgassing becomes more plausible. Yet neither can be ruled out solely by appearance because weak activity can be hard to detect, and a faint object can hide subtle coma in modest data. Therefore, analysts use a combination of dynamical and physical constraints. A useful test is whether the implied area-to-mass ratio is plausible for a natural small body. Brightness gives a hint of size, but size depends on reflectivity, and reflectivity is often unknown. An object could be small and bright or larger and dark. If dust contributes to brightness, the nucleus could be much smaller than implied. Thermal infrared measurements can help because they measure emitted heat, providing a more direct constraint on size. If size can be bounded, and if density can be assumed within a plausible range, mass can be estimated. The expected radiation pressure acceleration can then be compared to the inferred acceleration from residuals. If matching the residuals would require an implausibly low density or an extreme structure, radiation pressure becomes less likely as the dominant cause. If the required parameters fall within plausible ranges, radiation pressure remains a viable mechanism. However, sunlight rarely acts only on the nucleus. It acts strongly on dust grains released from the nucleus. Dust grains are small enough that radiation pressure competes with solar gravity and can dominate their motion. This is why dust tails form and point roughly away from the sun. The dust does not usually carry the nucleus with it, yet the dust can dominate the observed light. If the nucleus is faint and a dust cloud is bright, the measured position is pulled toward the brightest region of dust. This creates a centroid bias. The bias can be stable if the dust distribution is stable, and it can change with time if dust production changes or if viewing geometry changes. The result can be a residual pattern that resembles a radial acceleration even if the nucleus follows gravity, plus a different set of forces. In other words, sunlight can create an apparent acceleration by shaping dust that biases the measurement without necessarily creating the same acceleration on the nucleus itself. The orientation of the dust tail relative to the line of sight matters. A tail that lies mostly behind the nucleus in the plane of the sky will pull the centroid in the tail direction. A tail that lies mostly along the line of sight will contribute less to an apparent shift. As geometry changes, the projected tail direction changes, and the centroid bias can change. This can produce a residual pattern that varies with phase angle, the angle between sun object and observer. Phase angle also affects brightness because dust scatters light differently at different angles. In some cases, dust can forward scatter strongly, producing a sudden brightening when phase angle is favorable. Such a brightening can be misinterpreted as a surge in activity. If the brightening is geometric rather than physical, the dust production may not have changed, but the centroid bias could still change because the brighter dust becomes more influential in the measurement. Therefore, dynamical interpretations must be aware of scattering geometry. A related mechanism is that radiation pressure can separate dust grains by size. Smaller grains are pushed more strongly and spread out more quickly. Larger grains stay closer to the nucleus. This creates a tail with structure. If the observing aperture includes different parts of the tail depending on seeing and on measurement method, the measured centroid can vary. The same object can yield slightly different astrometric positions depending on how different observers measure it. This heterogeneity can appear as residual scatter or as a systematic difference between data sets. Again, this does not imply the nucleus changes its trajectory. It implies the measurement traces a moving brightness distribution rather than a single point. Radiation pressure on a very small nucleus can also be time variable if the nucleus rotates and presents a changing cross-section. For an elongated body, the projected area facing the Sun changes with rotation modulating the force. If rotation is stable, the modulation averages out over times longer than the rotation period. If observations sample the rotation unevenly, a small systematic bias could appear. In most cases, this modulation is subtle compared to measurement noise, but for unusually low-mass bodies, it could be detectable. The presence of tumbling would make the modulation more complex. These considerations tie radiation pressure back to the object's physical character, including shape and spin. There's also a thermal aspect to dust that links to radiation pressure. Dust absorbs sunlight and heats, and it re-emits infrared radiation. For small grains, thermal emission can contribute to forces like Poynting-Robertson drag, which slowly alters their orbits. This is usually relevant for dust evolution over long times rather than for nucleus motion over weeks, but it matters for how the dust environment changes and therefore for how centroid bias evolves. The dust cloud may thin or spread, altering the brightness distribution and shifting the measured center. In a long observing campaign, this evolution can create slow drifts in measured position that might be mistakenly interpreted as a dynamical acceleration. To test whether sunlight-driven dust bias is dominating observers, look for dependence on measurement method. If astrometric positions change when the aperture size changes or when the centroiding algorithm changes, extended dust is influencing the result. If deeper imaging shows a tail or asymmetric coma aligned with the direction of residuals, the case strengthens. If the object appears point-like in high-resolution images and residuals remain, then dust bias becomes less likely and direct forces become more relevant. In that case, radiation pressure on the nucleus itself can be evaluated via area-to-mass considerations. In the language of the title, an object that was waiting could be imagined as something held in place. In physics terms, sunlight does not hold an object, it pushes it gently. The impression of waiting can arise if the measured positions drift in a way that keeps the object near a predicted region or near a certain sky area, but such impressions are not diagnostic. The diagnostic is whether the residual direction is consistently radial, whether it scales with solar distance, and whether it persists across high-quality nucleus-centered astrometry. If these conditions hold, and if the implied area-to-mass ratio is plausible, radiation pressure becomes a credible contributor. If the conditions do not hold, radiation pressure may still influence dust, but not dominate nucleus motion. Thus, this region treats sunlight as an influence that can be real in dynamics and also deceptive in measurement. The same physical agent that pushes dust into a tail can also shift the center of light, and the same agent that exerts a tiny force on a nucleus can appear larger if the nucleus is small. The analysis must therefore keep two parallel threads. One asks what force sunlight applies to the nucleus given plausible physical parameters. The other asks how sunlight shapes the dust environment and therefore the measured position. Only by separating these threads can residual patterns be attributed correctly. If the separation is successful, what remains is a clearer view of whether the object's motion requires a non-gravitational acceleration beyond outgassing and radiation pressure, leading to thermal recoil rotation dependence and the complex coupling between surface properties and momentum exchange that forms the next inward layer. If sunlight pressure and outgassing do not fully account for the residual pattern, or if their required parameters become implausible, the next inward mechanism is thermal recoil, the quiet push created when absorbed solar energy is re-emitted as infrared radiation in an anisotropic way. A small body is not a perfect radiator that emits equally in all directions at all times. Its surface has thermal inertia, meaning it warms and cools with delay. Its rotation carries warm regions into and out of sunlight. Its roughness creates facets with different illumination. When the surface emits heat, it emits momentum, and the recoil can produce a small acceleration. Over long times, this is known to shift asteroid orbits measurably. Over shorter times, it can still matter if the measurements are precise and if the object's size and spin place it in a regime where the acceleration is detectable. The thermal recoil story begins with heat balance. Sunlight arrives and is partly reflected and partly absorbed. The absorbed fraction depends on albedo, the reflectivity. A darker surface absorbs more and heats more. The heat then either conducts into the subsurface or radiates away. If conduction is significant, the subsurface stores heat and releases it later. The delay shifts the location of the warmest region relative to the point directly facing the sun. On a rotating body, this often means the warmest region occurs on the afternoon side rather than at local noon. When that warm afternoon region emits heat, the recoil pushes the body slightly in a direction related to the rotation and to the orbit. This is the core of the diurnal Yarkovsky effect. There is also a seasonal component. If the spin axis is tilted, one hemisphere can experience a season of stronger insolation and warming. The stored heat can be emitted later in a way that produces a recoil with a different direction than the diurnal effect. The balance between diurnal and seasonal components depends on rotation period thermal inertia and obliquity, the tilt of the spin axis. An object with a very fast rotation can average temperature around its equator, more evenly reducing the magnitude of the diurnal asymmetry. An object with very slow rotation can have large day-night contrasts, but may also have the warmest region closer to the subsolar point if thermal inertia is low. The precise behavior depends on parameters that are often poorly known for a newly discovered faint object. Thermal recoil is size-dependent in a fundamental way. The force scales with surface area and emitted energy, while acceleration scales with force divided by mass. Mass scales with volume and density. Therefore, smaller objects generally have larger area-to-mass ratios and can experience larger accelerations from thermal recoil, all else equal. Yet very small objects can also equilibrate temperature, quickly reducing thermal lag, and radiation pressure can dominate. There's a middle range, often in the meter to tens of meters regime, depending on properties where thermal recoil can be important. Without a direct size measurement, this range cannot be assumed. It must be bounded using brightness albedo assumptions and ideally thermal infrared observations. Thermal recoil also depends on shape and roughness. A rough surface with many facets can emit heat anisotropically in complex ways. Self-heating occurs when radiation from one facet warms another, altering the temperature pattern. Concavities can trap heat. Shadows can create sharp contrasts. These effects can change both the magnitude and direction of net recoil. Models exist that can compute these effects given a shape model, but shape models are rarely available for faint objects. Therefore, in many cases, thermal recoil is treated with simplified parameterizations or with plausible ranges rather than with detailed physical reconstruction. The key is consistency, whether thermal recoil in plausible ranges can account for the inferred acceleration direction and magnitude. The direction of thermal recoil in orbit terms often manifests as an along-track acceleration component, because the afternoon heating lags can create a thrust that slightly speeds up or slows down the object along its orbit depending on rotation sense. This along-track component can produce a drift in semi-major axis over time. Over the short span of a few months, the effect may appear as a small along-track residual drift rather than as a dramatic change. If residuals show a direction aligned with the object's motion and persist when the object appears inactive and point-like, thermal recoil becomes a candidate. If residuals are primarily radial and scale strongly with solar distance outgassing or radiation pressure may still be more likely. Yet geometry can mix these components in observed sky residuals, so careful fitting is required. Thermal recoil is coupled to spin state. A stable rotation with a known period produces a stable recoil direction in an averaged sense. A changing spin axis orientation changes the recoil direction. A tumbling state can reduce the net recoil by averaging emission over many orientations, or it can produce a time-variable recoil that is hard to model. Spin state can also change due to torques, including those from outgassing or radiation. This creates feedback. If the spin changes, the thermal recoil changes. If thermal recoil is being invoked to explain residuals, it becomes important to know whether the spin is stable. Photometric monitoring can help. A consistent light curve suggests stability. A shifting or multi-period pattern suggests tumbling. Without such data, thermal recoil remains plausible but unconstrained. To assess thermal recoil rigorously, analysts link the dynamical inference to plausible physical parameters. If an acceleration magnitude is inferred, the required emitted power asymmetry can be estimated. Emitted power is tied to absorbed solar power, which depends on size and albedo. If the required asymmetry implies more power than the object can absorb at its solar distance, thermal recoil is ruled out. If it implies a fraction of absorbed power emitted with a directional bias that is plausible given roughness and thermal lag, it remains viable. This is a grounded constraint. It uses energy conservation and known solar flux rather than speculation. Thermal recoil also interacts with surface changes. As a body approaches the sun's surface, temperatures increase and can cause physical changes, such as cracking dust migration or the release of volatiles. Even if outgassing is weak, these changes can alter thermal properties by changing porosity and dust layer thickness. A fresh surface can have different thermal inertia than an aged, dust-covered one. Therefore, thermal recoil might not remain constant over time. It could strengthen or weaken as the surface evolves. This variability could contribute to residual patterns that change slowly with time, complicating simple, constant parameter fits. In the frame of the title, weighting could be imagined as a body that remains poised, but thermal recoil is the opposite of poised. It is a continuous gentle push driven by the object's interaction with sunlight and its own rotation. If residuals persist and do not correlate with visible activity, thermal recoil provides a physically ordinary explanation that does not require gas production. Yet because it depends on poorly known parameters, it must be treated as a constrained hypothesis rather than as a convenient fallback. Its plausibility rises when the object appears inert and point-like, when the inferred acceleration direction is compatible with a long-track drift, when photometry suggests a stable spin, and when size and albedo constraints allow sufficient absorbed energy. At the end of this region, thermal recoil stands as a candidate mechanism that ties the object's trajectory to its physical character through heat and momentum. It does not demand that the object be special. It demands only that it be small enough and oriented in a way that produces a measurable recoil. The next inward step is to focus on rotation state and irregular shape more directly, because these are the factors that decide whether thermal recoil is steady or variable, whether outgassing jets average out or create directed thrust, and whether the measured positions can be trusted to trace the nucleus or are being pulled by changing brightness structure. In that deeper layer, the motion becomes inseparable from the object's physical form, and the concept of weighting becomes a question not of intention, but of how a rotating, irregular body can appear to linger when forces and measurement biases interact over time. The next inward layer is the object's rotation state and shape, because these are the hidden variables that control how non-gravitational forces average over time, and how the object's light distribution shifts in the images. A small body is rarely a smooth sphere. It is a chunk of material with ridges, facets, pits, and sometimes multiple lobes. Its spin can be regular or chaotic. This physical complexity determines where sunlight is absorbed, where heat is stored, where gas escapes if volatiles exist, and how dust is released and shaped. It also determines whether the forces discussed earlier remain steady enough to be captured by simple models, or whether they vary in direction and magnitude in ways that produce residual patterns that seem inconsistent until the object's orientation is considered. Rotation is inferred most commonly through photometric light curves. As the object spins, its projected area changes and the brightness changes. A repeating pattern suggests a stable rotation around a principal axis. The period can be measured in hours or days, depending on the object. The amplitude of the light curve gives hints about elongation, because a more elongated object tends to show larger brightness variation as it rotates. A complex light curve that does not repeat cleanly can indicate tumbling, meaning rotation around more than one axis. Tumbling changes the object's orientation in a non-repeating way over the timescale of observations, and this has direct consequences for force modeling. A thrust from a localized jet or an asymmetric thermal emission pattern depends on orientation. If the orientation is changing irregularly, the net acceleration can change irregularly. Shape and rotation are coupled through inertia. An elongated body has different moments of inertia about different axes. If it is disturbed, it can enter non-principal axis rotation. Over time, internal friction can damp tumbling and settle the rotation into a stable state. But the timescale depends on internal structure. A rubble pile, a loose aggregate of rocks and dust, can dissipate rotational energy through small internal shifts. A monolithic fragment can be more rigid and dissipate energy more slowly. Structure is rarely known directly, but its influence appears indirectly in how stable the rotation is and how quickly the spin state changes when torques act. Torques are present. Outgassing jets can exert torque if they emerge from a region that does not pass through the center of mass, which is most regions on an irregular body. Radiation pressure can exert torque as well, because sunlight reflected and re-emitted from an irregular shape does not act symmetrically. These torques can change rotation period and can tilt the spin axis. A changing spin axis changes which surface regions receive sunlight over time, altering both outgassing patterns and thermal recoil. This creates a feedback forces change, spin changes forces. If the residual pattern changes with time, such feedback is one possible explanation. The rotation state also shapes the interpretation of residual direction. A steady average acceleration away from the sun suggests a radial force such as radiation pressure or average outgassing. A steady along-track acceleration suggests thermal recoil or an offset outgassing thrust. But if the object's spin axis is tilted or evolving, the average thrust direction can include components that vary. A localized jet can produce a thrust component out of the orbital plane, generating normal acceleration. If residuals show out-of-plane behavior, and if activity indicators are present, a localized jet tied to rotation becomes plausible. Yet without rotation constraints, the same residual pattern could also be created by centroid biases that depend on coma structure. Rotation matters there too, because coma asymmetry can rotate with the nucleus, creating periodic shifts in the measured position. A critical observational clue is periodicity in astrometric residuals. If residuals show a repeating pattern with a period matching the light curve period, it suggests that the measured position is modulated by rotation-dependent brightness structure. This could be a rotating jet or an asymmetric coma. In such a case, the orbit fit might interpret the modulation as noise or as a weak acceleration, but the true cause would be a shifting center of light. A rotating asymmetry can shift the centroid back and forth around the nucleus. Over time, this can produce an apparent drift if observations sample the rotation phase unevenly, because the average centroid offset in the sampled phases might not be zero. Therefore, even when the nucleus motion is purely gravitational, rotation-dependent coma structure can create a residual pattern that looks like a small acceleration. This is a subtle pathway from physical behavior to measurement artifact. Shape also affects thermal recoil in a way that can change the sign or magnitude of the effect. The thermal emission pattern depends on which facets are warm and how they are oriented. For a rough surface, small facets can emit preferentially in certain directions. Self-shadowing changes when a facet receives sunlight. The net recoil can therefore be sensitive to spin axis orientation and to the distribution of roughness. If the object tumbles, the thermal recoil might average down. If it rotates stably, the recoil might persist. If the spin axis precesses slowly, the recoil direction might drift over time. These behaviors could produce residual patterns that change on timescales of weeks or months. A simple, constant parameter thermal model might fail, leading to residuals that appear inconsistent unless the changing spin state is considered. Rotation also influences outgassing in a direct way. If volatiles exist in localized patches, They may be illuminated only during certain rotation phases. This produces jets that turn on and off. The time-averaged thrust depends on how long the patch is illuminated and on thermal lag. If the patch is near the equator of a tilted spin axis, seasons can change its illumination fraction. If the patch is near a pole, it might be illuminated for long intervals. Therefore, even at constant heliocentric distance, outgassing thrust can vary because orientation changes. Such variability can make an object appear to behave unpredictably in residuals. Yet the behavior remains physical and tied to geometry and heat transport. In some cases, rotation changes can lead to surface failure. If a torque spins the object up, centrifugal forces increase. For a weakly bound rubble pile, this can cause mass shedding. Mass shedding releases dust, increasing brightness and altering coma structure. It can also change the object's shape and moment of inertia, changing rotation further. A small shedding event can also expose fresh material, potentially increasing outgassing. The orbit might then show a time-variable acceleration, and the astrometry might show time-variable centroid bias, both linked to the same physical event. If an object is described as waiting and then changing, such an interpretation could be reframed as a transition in surface state, driven by spin and solar heating, not by intention. To use this layer effectively, observers aim to measure rotation. They gather photometry over many nights, seeking a stable period. They look for changes in period that would indicate torque. They look for irregularities that indicate tumbling. They compare these findings to residual patterns. If residuals vary in sync with rotation measurement, bias is implicated. If residuals drift smoothly independent of rotation, dynamical forces may be dominant. If both occur, both are present. The object is then understood as a physical system whose state evolves. This inward layer therefore changes what it means to say the object was never passing through. The phrase can be translated into the possibility that the object's apparent residence and residual behavior are shaped by a combination of low relative motion geometry and time-variable non-gravitational effects whose direction depends on rotation. The object may remain observable in a region while its rotation-dependent forces add small departures from the baseline. The departures can complicate orbit classification near the bound-unbound boundary, and they can create a persistent impression that the object is not simply following a passive path. Yet the measurable content remains in residuals, photometry, and morphology. Rotation and shape are the hidden drivers that can make ordinary mechanisms look puzzling when viewed only through orbital elements. Once they are considered, the remaining puzzle is not about physics failing. It is about which rotation state and which surface properties are present, and how strongly they couple to sunlight heat and any volatile release. With the object's physical complexity acknowledged, the next inward check returns to gravity in a different way by asking whether the gravitational environment has been fully accounted for and whether any overlooked interactions could create the impression that the object is not merely passing through. The baseline includes the Sun and planets, but in precise work, the solar system is a crowded gravitational field with many small contributors. Most of these contributors are too weak to matter, but some can matter at the edge of modern measurement precision, especially if the object passes through regions where certain masses are concentrated, or if the orbit solution is sensitive near a classification boundary. The first gravitational question is whether any close encounter has occurred with a planet or a major moon. A close encounter is not mysterious. It produces a predictable change in trajectory. Yet if the orbit is uncertain early on, an encounter can be overlooked, because the predicted close approach distance might shift as new data arrive. This could produce the appearance that the object's path changes, when in fact the path was always influenced by a close approach that was not recognized in early solutions. In refined work, analysts propagate the orbit backward and forward with uncertainties to identify possible close approaches and their range of distances. If the object has an approach within a distance, where gravity would create a measurable deflection, that deflection is included and the baseline becomes more accurate. If no close approach exists, the baseline is simpler and attention shifts away from gravitational deflection. Beyond the major planets, the largest asteroids can matter in specific contexts. The main belt contains the most massive asteroids, and their combined gravitational influence can produce small perturbations on objects that travel through or near the belt over long arcs. For many purposes, these perturbations are negligible, but when residuals are small and coherent, and when the observation arc is long, even small omitted terms can become relevant. Analysts may include a set of massive asteroids in the integration and test whether the residual pattern changes. If it does, the anomaly may be gravitational after all, not because gravity is new, but because the baseline was incomplete for the precision required. There is also the possibility of a very close pass near a smaller body, such as an asteroid, that is not among the massive set typically included. Such events are rare because space is large, but they are not impossible. A close pass could produce a small deflection that might be hard to recognize if the other body's ephemeris is uncertain. However, this hypothesis requires evidence because invoking an unknown close pass without constraints can become an unfalsifiable escape. Therefore, analysts treat it as low priority unless the residual pattern suggests a specific timing and magnitude consistent with a brief gravitational impulse, and unless a plausible candidate body can be identified in the relevant region. The emphasis remains on what can be checked. Another gravitational subtlety is the role of reference frames and barycentric motion. Planetary ephemerides and orbit integrations can be carried out in a barycentric frame where the origin is near the solar system's center of mass. In such a frame, the Sun itself moves slightly due to planetary tugs. If frame transformations are mishandled, or if timescales are misaligned, small systematic errors can appear. These errors can create apparent residual drifts that mimic accelerations. Therefore, part of gravitational completeness is computational completeness. Analysts compare independent orbit determination software and independent ephemerides to ensure that the gravitational baseline is implemented correctly. Agreement across independent implementations reduces the chance that an anomaly is an artifact of coordinate or timing conventions. A different gravitational pathway toward apparent anomalies comes through tides and physical response, rather than through center of mass acceleration. If an object passes relatively close to a planet, tidal forces can stress it. Tidal forces do not change the center of mass orbit beyond what gravity already predicts, but they can alter the object physically. Stress can open cracks or trigger mass shedding. If mass shedding occurs, dust production increases and centroid bias can change. If fresh surfaces are exposed, outgassing could increase. In this way, gravity can indirectly create a non-gravitational signature by causing a physical change that then drives outgassing or alters the measured centroid. This chain remains within ordinary physics, but is easily misread if the physical event is not observed. A sudden shift in residuals accompanied by brightening might indicate such an event, and its timing relative to any close approach can be examined. Binarity and fragmentation provide another inward check. If the object is actually a binary, two bodies orbit each other, and the combined light distribution can shift as their separation and brightness ratio change. Even if the barycenter follows gravity, the center of light can move periodically. This can create residual patterns that look like a dynamical wobble. Fragmentation can create multiple pieces, and if one piece dominates brightness, the measured position can jump as dominance shifts. Both scenarios can create the impression that the object is not following a single trajectory. Detecting these requires imaging light curve anomalies or other evidence. In the absence of evidence, they remain possibilities, but not conclusions. Yet they matter because they demonstrate how an object can look as if it is resisting prediction, when in fact the prediction is being compared to a measurement that does not correspond to a single stable physical point. Gravitational resonance behavior is another concept that can be mistakenly tied to the idea of weighting. In some configurations, a small body can share an orbital period with a planet, or can be trapped in a resonance that causes its relative motion to the planet to remain bounded. Such objects can appear to linger near certain relative longitudes over long times. In the case of co-orbital motion, a body can share a planet's orbit and remain near a stable region relative to it. Translating weighting into this kind of dynamics requires strong evidence because resonance is a long-term property. The measurable test is to integrate the orbit under gravity forward and backward and examine whether the relative angles and semi-major axis remain in resonance. This requires a well-constrained orbit and often requires accounting for non-gravitational forces if they are present. Without such analysis, resonance language is premature. But the existence of these dynamical states shows that resonance-like behavior can be purely gravitational and does not require any failure of physics. When the gravitational environment is fully accounted for, and when computational and data association pitfalls are controlled, whatever residual pattern remains becomes more trustworthy as a physical signal. Yet even then, the signal may not demand an exotic interpretation. It may demand a more complex combination of known non-gravitational forces or a more careful handling of centroid bias. The gravitational completeness check therefore serves a clear purpose. It removes the possibility that the object's apparent deviation or residence is simply a product of missing gravitational terms or misapplied frames. It also reminds that gravity can indirectly trigger physical changes that then create non-gravitational signatures. At this depth, the phrase "never passing through" is again translated into measurable outcomes. A bound orbit, perhaps resonant, would mean return or long-term residence. An unbound orbit would mean passage. A small non-gravitational acceleration could shift the classification near the boundary. A fragmentation or binary could confuse what is being measured. Each of these is testable in principle. The next inward region is therefore not about adding new physics, but about stating what is currently constrained and what remains ambiguous, and about emphasizing prediction tests and multimodal observations as the path to clarity. If the object appears to wait, the disciplined approach is to ask which measurable dynamical state or observational bias produces the appearance, and which additional measurements would distinguish among the ordinary mechanisms that remain. At this point, the remaining task is to state clearly what it means for the current model set to be insufficient, and to prevent a gap between fit and data from turning into a claim about intention. This region treats explanation as a hierarchy. At the outer levels, explanation means the object is real, tracked, and predictable under a baseline. At intermediate levels, explanation means residuals are understood as measurement systematics or as known non-gravitational forces. At this deeper level, explanation means the remaining uncertainty is located precisely which parameters, which mechanisms, and which data limitations prevent a unique account. The phrase "it was waiting" is then handled as an interpretive label that must be replaced by measurable alternatives, such as low relative motion geometry resonance, like behavior, or persistent non-gravitational acceleration that keeps the object's apparent position from matching a simple baseline. A common reason for apparent stubbornness in the data is model degeneracy. When multiple mechanisms can produce similar residual signatures over the available time span, the fit cannot uniquely assign cause. For example, a weak radial acceleration away from the Sun could be produced by radiation pressure on a low-mass body, by an outgassing thrust that is roughly anti-sunward, or by a centroid bias caused by a dust tail that pulls the measured position anti-sunward. Over a limited geometry range, the sky residuals produced by these scenarios can look similar. Even in a long-track drift can be produced by thermal recoil or by an outgassing thrust with an offset direction. If the observations do not include independent evidence of activity size and spin, the dynamical inference alone can support more than one explanation. In that case, the correct statement is not that the object behaves inexplicably. The correct statement is that the current data allow more than one physically plausible model. Another reason is time-variable forces. Standard non-gravitational parameterizations often assume smooth functions of heliocentric distance, but real bodies can have forces that change with rotation, with surface evolution, and with episodic events. If the object experiences a small outburst, the thrust history is not smooth. If the object tumbles, the direction of thrust or thermal recoil changes. If dust production changes, centroid bias changes. A smooth acceleration model will then fit imperfectly, leaving residual structure. The residual structure does not imply new forces. It implies the force history is more complex than the model. Without continuous monitoring, the difference between smooth and episodic behavior can be hard to detect, and the model can only approximate. A third reason is that the data set may not be self-consistent in what it measures. Astrometry is often assumed to measure the nucleus. In reality, it measures the brightest point or the centroid of a brightness distribution. If the brightness distribution changes, the measured position changes even if the nucleus follows a smooth path. This can occur if the object develops a coma, if the tail becomes prominent, or if an asymmetric dust feature rotates. In such cases, the orbit fit is being asked to explain a moving measurement target. It will not succeed fully because the model integrates a point mass, not a shifting light distribution. The right response is to obtain nucleus-centered astrometry, or to model the coma and correct the centroid, not to infer a failure of dynamics. This region therefore emphasizes prediction as the strict test. If a model that includes an additional acceleration improves forward predictions consistently, it is a strong sign that the acceleration reflects a real systematic in the motion, or a stable systematic in the measurement. If the model improves fit to the existing data but does not improve prediction, it may be overfitting or compensating for data artifacts. Prediction requires new data, and it provides an external check. In the context of the title, a sense that the object is waiting often arises because it remains in view, and because repeated predictions are updated. The discipline is to separate the ordinary iterative refinement of prediction from a true inability to predict. Precision also demands realistic uncertainty. If measurement uncertainties are underestimated, residuals appear more significant. If they are overestimated, real signals can be hidden. Analysts therefore examine the residual distribution check for outliers and adjust weights. They may use robust methods that reduce sensitivity to outliers because a small number of biased points can create a spurious drift. They also compare independent reductions. If different teams using different pipelines reach the same residual pattern, confidence increases. If they do not, the anomaly may be procedural. The measurable translation of weighting is now constrained to a small number of scenarios. One is a geometry-driven residence where apparent motion is low and the object stays in a region because of relative velocity and elongation. This can be quantified directly from the orbit and the observer geometry. Another is resonance or co-orbital behavior, where relative angles remain bounded over long times, which can be tested by long-term integrations, and is meaningful only if the orbit is well determined. Another is persistent non-gravitational acceleration, which can be quantified as a fitted term with direction and distance dependence. Another is persistent centroid bias, caused by dust, which can be tested by imaging and by method dependence. Each scenario is compatible with physics and does not require intention. Each scenario points to specific observational needs: more astrometry over a longer arc, deeper imaging to resolve coma photometry, to measure spin spectra, to constrain gas thermal data, to constrain size, and multiple independent pipelines to confirm robustness. In this region, it becomes important to state what remains uncertain without speculation. If the orbit classification between bound and unbound is sensitive to non-gravitational terms, that sensitivity must be stated. If the residual pattern could be explained by either radiation pressure or dust bias, that degeneracy must be stated. If the object's size is uncertain because brightness may include dust, that uncertainty must be stated. The goal is to make uncertainty concrete. Concrete uncertainty is not indecision. It is the accurate boundary of what the current data can support. This also reframes why certain titles can feel compelling. The human mind expects that motion through space should be simple. When the measured track departs from a simple model, it invites stories. Yet the solar system is a place where small bodies are governed by gravity, plus small forces tied to sunlight and volatile release, and where measurement is governed by photons and algorithms that trace brightness, not mass. The correct response to residual structure is not to step outside physics. It is to step further into the details that physics already predicts should matter. That is the inward move. It replaces a vague claim with a set of constraints that can be tightened. By the end of this region, the object's situation can be described as follows in a disciplined way. A gravity-only baseline produces a certain residual structure. The measurement chain has been audited for biases. Standard non-gravitational mechanisms have been considered. The remaining mismatch, if any, is either within uncertainty or it is significant but degenerate among several plausible causes. The next step is not to assert weighting. The next step is to prioritize decisive tests that reduce degeneracy. If the object continues to be observed, those tests will occur naturally through improved arc and through targeted observations. As the arc grows, the difference between a true acceleration and a measurement bias becomes clearer. As physical constraints improve, the range of plausible mechanisms narrows. In that narrowing, the object's behavior stops being described by evocative words and becomes described by fitted parameters, observed morphology, and the predictive success of models. That is the form of explanation that remains faithful to the sky and to the physics that governs it. The final inward step gathers what is now constrained and turns it into a practical set of next measurements and interpretive boundaries that prevent the story language from outrunning the evidence. By this stage, the object is no longer merely a moving point in survey footage. It is a tracked body with a refined orbit solution, a residual history, and at least provisional physical hints from brightness behavior and image morphology. The key question is whether the appearance of weighting is best explained as geometry, as dynamics, or as measurement bias. The answer is not chosen by preference. It is chosen by which explanation improves prediction and remains consistent with independent observations. If the orbit under gravity alone fits the astrometry within realistic uncertainties, once systematics are controlled, then the object is behaving as a passive test particle to the level that can currently be measured. In that case, any sense that it was never passing through is an artifact of how the observation window intersects its motion. The measurable interpretation becomes residence in observability. It remained detectable for an extended interval because its elongation from the sun and its apparent angular speed kept it in surveyable sky regions, and because the observing network followed it with dense cadence. This is a genuine and measurable form of presence, but it is not a dynamical state that implies stasis. The object still moves along its orbit. The weighting is in the human sense of attention and visibility, not in the mechanical sense of altered motion. If residuals persist coherently beyond uncertainty and across independent instruments, then an additional term is required, but the term must be described precisely. A fitted acceleration should have a direction in an orbital frame, a distance dependence, and a timescale. Its magnitude should be compared to what known mechanisms can supply. If the direction is largely radial and away from the sun, radiation pressure and anti-sunward outgassing become candidates, and dust centroid bias remains a confounder. If the direction is a long track, thermal recoil or an offset outgassing thrust becomes more plausible. If the direction varies, rotation-dependent forces or centroid shifts become likely. In each case, the best model is the one that improves forward prediction because prediction is the test that prevents a model from merely absorbing past noise. The decisive observations that sharpen this choice are concrete. High-resolution imaging at multiple epochs can determine whether the object is point-like or extended, whether a coma or tail exists, and how that structure changes. Imaging also allows tests of centroid dependence on aperture. If the measured position shifts with aperture or with centroiding method, the data are not tracing the nucleus cleanly, and any inferred acceleration must be treated with caution. Spectroscopy can search for gas emission or set upper limits on production rates. These limits can be compared to the thrust required by an outgassing model given plausible size and mass ranges. Thermal infrared observations can constrain size and albedo tightening mass estimates, and therefore tightening the plausibility of radiation pressure and thermal recoil. Photometric monitoring can determine rotation period, detect tumbling, and detect changes in spin that would indicate torques. If rotation is stable, averaged force models become more plausible. If rotation is complex, time-variable force histories and centroid modulation become more plausible. Longer arc astrometry remains the simplest and often the most powerful constraint. Over time, degeneracies weaken. A true non-gravitational acceleration produces a consistent divergence between gravity-only predictions and observations that grows in a predictable way. A measurement bias often changes with observing geometry, instrument, or brightness structure, and may not accumulate in the same stable way. As the object moves through different star fields and is observed at different air masses and phase angles, systematics can be diagnosed. The object's continued motion provides natural experiments. If the same residual pattern persists under changing conditions and across independent pipelines, the case for a dynamical acceleration strengthens. If the pattern changes or dissolves, the case weakens. If resonance or co-orbital behavior is proposed as a translation of weighting, that too requires a specific test. The orbit must be integrated under gravity over a long interval with uncertainties propagated to see whether the relative motion to a planet remains bounded or whether the orbit is simply passing through. Such a test is meaningful only when the orbit is well constrained and when any non-gravitational accelerations are either shown to be negligible or included as plausible ranges, because small accelerations can alter long-term resonance behavior. Therefore, resonance interpretations must come late, not early. They are an inward conclusion, not an outward impression. The object's classification, as bound or unbound, must also be handled with this same discipline. If the gravity-only orbit lies near the boundary, non-gravitational forces can shift the inferred eccentricity. An object that appears slightly hyperbolic under gravity. Only fitting could become consistent with bound motion when a small outward acceleration is included, because the fit changes the inferred energy. Conversely, an object that appears bound could be nudged toward unbound in a different modeling assumption. The correct practice is to state the sensitivity, how much non-gravitational acceleration would be required to change classification, and whether that acceleration is physically plausible given the object's observed properties. This sensitivity statement replaces dramatic certainty with a constrained range. It also prevents the story that the object was never passing through from becoming detached from the fact that classification depends on model assumptions. By the end of this final section, the story language is fully translated. Weighting becomes one of three measurable states. It can be a visibility residence created by geometry and survey cadence. It can be an apparent residence created by shifting center of light measurements in the presence of dust or asymmetric structure. Or it can be a dynamical divergence created by a small additional acceleration due to outgassing radiation pressure or thermal recoil, perhaps modulated by rotation. None of these states requires intention. Each state has a measurable signature. Visibility residence is seen in slow, apparent angular motion and prolonged safe elongation. Center of light shifts are seen in morphology, aperture dependence, and correlations between residuals and brightness structure. Dynamical divergence is seen in persistent residual drift that survives instrument and pipeline diversity and improves prediction when modeled as an acceleration. The final practical boundary is that any explanation must be predictive and cross-validated. It must work not only for one subset of data, but across multiple observatories. It must not depend on a single reduction choice. It must not vanish when images are reprocessed or when suspect points are removed. It must not require physical parameters that violate energy balance or plausible material properties. When these boundaries are applied, what remains is a narrow set of ordinary mechanisms that can be tested with targeted observations. The object then stops being described as if it is waiting. It is described as a small body with a particular orbit, and with a constrained set of forces acting on it, moving through space according to measurable rules and appearing to linger only to the extent that geometry, sunlight, and measurement define what can be seen and how precisely it can be tracked. The tracking continues beyond the formal boundary of the sections, not as an extra chapter, but as the same patient accumulation that begins with discovery. The object's next positions either land where the refined model predicts, or they do not, and each new point reduces the room for interpretation. If predictions hold, the sense of waiting resolves into a visibility story. The object remains in favorable geometry, and the observing network keeps it in view so it feels present for a long time. If predictions drift, the drift is either a stable offset that can be parameterized as a small acceleration, or it is a pattern that changes with instrument air mass aperture and morphology pointing back to measurement and to the shifting center of light. The decisive narrowing comes from multimodal constraints arriving together. A point-like appearance under high-resolution imaging pushes against coma-driven centroid bias. A detected coma or tail, especially with asymmetry aligned to residual direction, makes centroid bias and outgassing more plausible. A stable light curve period without complex modulation supports steady averaging of forces. A tumbling signature supports time-variable force direction and time-variable centroid modulation. A thermal size estimate tightens mass and therefore limits radiation pressure and thermal recoil to specific ranges. Spectroscopic upper limits on gas production tighten how much outgassing thrust is feasible. As these constraints tighten, the residual pattern stops being a canvas for dramatic phrasing and becomes a set of numbers tied to specific mechanisms. In that final framing, the object is not treated as a visitor that chooses to pass or not pass. It is treated as a small body whose motion is the sum of gravity and small additional effects that depend on sunlight, heat, surface state, and measurement practice. If the object remains in view, it is because its orbit and the Earth's vantage create a long window of detectability. If it deviates slightly from a gravity-only path, it is because momentum is exchanged through gas dust or photons, or because the measured centroid is not the nucleus. The sense of weighting becomes a shorthand that dissolves once the geometry and the forces are described, precisely leaving only what the sky permits to be measured and what the model must match.